Goal 11 is describing how the vector nature of momentum affects the law of conservation of momentum. And 12 is to use your understanding of vectors to show what happens after a collision. Okay, so we are going to be using these graphs. First of all, a couple things you want to notice. Cart 1 is the triangles. Cart 2 is the gray line. Okay, so we know the difference between the two carts. The questions are on the back of the next page. So we have 25 through 28. And it says, which graph shows a cart explosion? And what that means is both carts are going to be at rest, and then they are going to move apart when the spring is released. And then it wants to know which graphs show an inelastic collision. So what I'm going to do right now is I'm going to label these carts. We'll label this one cart A, or sorry, graph A, B. This is the front side. So A, B, C, and D. So A, B, C, and D. Okay, so the explosion is when both carts are at rest. Now notice in the beginning here, for all this time, I only see like the triangles. That's because the gray cart is also on this side, right? So both carts are at rest here, okay? For this one, I can see that cart 1 this is velocity. This is at 10 meters per second. And cart 2 here is at 0, so cart 2 is at rest, is at 0 meters per second. Let's turn the page. For this one, this is also velocity, and if we take a look here, this is actually 0, and I can see here's cart 2 coming off of that and cart 1, so these are both together. So both carts are at rest, so they're both at 0 meters per second here. And then for cart D, I can see that cart 1 is at 10 meters per second. And if you take a look here, you see how this is coming up. It's kind of hard to see because of the gray line, but there is a gray line down here. So this is cart 2 is at 0 meters per second. So in order for it to be an explosion, both carts are going to be at rest, and that happens in the beginning. That happens for A and for graph C. So this is A and C. And then the other two graphs show an inelastic collision because the carts are at different velocities and then they stick together for a new velocity. So here they're sticking together, new velocity. So this is this is graphs B and C. All right, so which graph are the masses of the carts equal? Okay, the masses of the carts equal is if their change in velocities are the same. So let's take a look. So here, both carts start at rest, and when they explode, this cart 1 goes up to 7 meters per second, and we take a look at cart 2, and it goes down to -7 meters per second. The only way that their change in velocity can be the same is if their if their momentum is the same for both. So that means their masses also have to be the same, because I know that beforehand momentum, mass times velocity, is 0. So I know here mass times velocity, when I add them together, has to be 0. So if I have 7 and -7, that means whatever my masses are has to be the same. So if the mass was 4, then this would be 28 and -28 for the momentum, which equals 0 for the total momentum. So cart A, their masses are the same. Let's take a look at this one. So for cart B, let's look at their change of velocity here. So I started at 10, right? And then their new velocity, so both carts are now at 5 meters per second. So what's happening then is I'm going from 10 to 5. So my change in velocity here, I'm losing 5 meters per second. Okay, so it started at 10, it's now at 5. And then here if I go, I'm starting at 0, right? And then I'm going to 5. So my change in velocity here, 5 minus 0, is going to be positive 5 meters per second. So again, if I try to do the momentum equal the momentum after, because these are equal and opposite, right? Equal and opposite change of velocity, then B is going to be also the same mass. We come up to here, so we start at 0, and cart 1 is now at 2 meters per second, and cart 2 is at negative 8 meters per second. Now they started at 0, so the change in velocity for cart 1, 2 minus 0 is 2 meters per second. The change in velocity for cart 2, since I'm at 0 to negative 8 minus 0, that change in velocity is negative 8 meters per second. And what that tells me is that their masses cannot be the same, because when I add these two momentums together, they have to equal 0. So I have to multiply by different masses to get the same numbers. So that is not true for this one. And then for the last one, D here, the carts, so both carts end up sticking together, and they are now going 7 meters per second. All right, well 7 is the final velocity minus 10, so the change in velocity for cart 1 is negative 3 meters per second. And the change in velocity for cart 2, I started at 0 and I went to 7, so 7 minus 0 is 7 meters per second. These are not equal and opposite, so the masses cannot be the same. All right, what is the velocity of cart 2 in graph 4? So this is my graph D. So we found this already. If we take a look at graph D, the change of velocity is positive 7 meters per second for cart 2. All right, for 28, we don't have a graph 6, so we're going to change that and we're going to make it graph C. And what we want to know is if the cart has a mass of 0.5 kilograms, what is the momentum in cart 1? And we're going to go graph C, so that's your third graph, after the collision. So let's take a look. We know the mass, but for momentum, we need the mass and the velocity. So if we come up to graph C, right, for cart 1, the momentum or the velocity is 2 meters per second after the collision. Remember, it was at 0, but now it's 2. So then down here, we're going to go 0.5 kilograms times 2 meters per second, and then if you type that in your calculator, you get 1 kilogram times meters per second.